Object-oriented programming is a programming paradigm that goes all the way back to the 1960s. It first appeared in a form that we might recognize today in a language called Simula 67. It was such a potent idea that it was quickly adopted by other languages, most notably Smalltalk, Object Pascal, and C++. Most modern programming languages, including JavaScript, have origins in these languages. What object-oriented programming is depends on who you ask, though there are some features that appear in almost every definition of object-oriented programming. They are dynamic dispatch, polymorphism, encapsulation, and inheritance. We'll be learning more about these things as we go along. Dynamic dispatch determines which code is to be executed at any given time. Polymorphism allows like objects to be treated similarly. Encapsulation allows like data and functionality to be bundled together, and inheritance allows objects to be specialized or generalized. Before we dive into each of these terms in detail, let's consider a layperson's definition of object-oriented programming. Once we have that, it'll be easier to discuss these features. Object-oriented programming is a way of logically organizing your code in a way that makes sense with respect to the problem we're trying to solve. As the name implies, at the heart of object-oriented programming is the concept of an object. The easiest way to start thinking about objects is to make real-world analogies. A car is an object, a shape is an object, a person, considered abstractly, is an object. Once you start thinking about real-world things as objects, you can start thinking about their parts and relationships. A car is a type of vehicle. It has a certain number of wheels, and it has functionality. It moves, lights up, etc. A triangle is a shape, and shapes have a certain number of sides, possibly infinite, such as a circle. Object-oriented programming allows you to express, in code, these relationships and properties. Let's take a look at what classes and objects mean. Classes are abstract representations of things. A vehicle, but not a specific vehicle. A car, but not a specific car. You can think of classes as templates. Objects, or object instances, are concrete things. A specific vehicle, such as my car, or Jim's car, or car 37. In most object-oriented languages, including JavaScript, it is conventional to start class names with capital letters and start object names with lowercase letters. On the left, we see a class hierarchy. Class vehicle is our most generic class, and gas vehicle and electric vehicle are subclasses of vehicles. Similarly, car is a subclass of gas vehicle. You can say that a car is a gas vehicle and it also is a vehicle, but a vehicle isn't necessarily a car. Note that most of our objects are instances of classes at the bottom of the inheritance tree: cars, motorcycles, and electric cars. However, you can usually have instances of any class. For example, we have generic vehicle 15, which is an instance of the vehicle class. What's important to understand about objects is that they inherit the functionality of not just their class, but that of their superclass and all ancestors. For example, if all vehicles have a property called odometer, then an instance of type car has an odometer because vehicle is one of its ancestors. A gas vehicle could have a property called fuel level, so car and motorcycle would also have fuel level, but an electric car would not because it is not an ancestor of either car or motorcycle. As you can see, object-oriented programming is very intuitive. We are logically modeling real-world behavior in a way that makes sense to us. This is one of the reasons that object-oriented programming has been so popular. If you're coming from a classically object-oriented language like Java or C++, JavaScript might be a little disorienting, as it takes a different approach to object-oriented programming. Let's look at some of the ways JavaScript is different from other object-oriented languages. In JavaScript, objects without classes are very common, generic objects. In most other object-oriented languages, you have to have a class before you can have a concrete object. Partially this is because there's no formal concept of a class in JavaScript. Classes are modeled by functions that create objects, which are essentially object constructors, as they are known in other languages. In JavaScript, there are no access modifiers, like public and private. JavaScript provides additional mechanisms for code reuse to make up for some of these deficiencies. JavaScript is prototypal, something we'll be talking about more later on. In JavaScript, methods can be evoked as if they belong to other objects or classes. And lastly, functions that aren't associated with an object can be evoked as if they were methods of an object. Now let's look at how JavaScript is similar to other object-oriented languages. Method and property access in JavaScript is mostly the same as most modern object-oriented programming languages. You just use a period to access the property or a method. JavaScript also provides an instance of operator, which is a common operator in other object-oriented languages. JavaScript does provide a mechanism for dynamic dispatch, meaning the correct method is applied at the correct time. And lastly, JavaScript does provide a method for polymorphism, although it's slightly different than the way it works in other languages. As we work through this course, some of the distinctions will make more sense to you. If you don't have experience with other object-oriented languages, don't worry. In a way, you're ahead of the game because you don't have any preconceptions to get in your way. If you do have experience with other object-oriented languages, I encourage you to approach JavaScript with an open mind. You don't have to unlearn anything you know about object-oriented programming, but your understanding of it will naturally be expanded. Broadly speaking, there are two ways to use JavaScript on your computer, in a browser or using Node. We will demonstrate both approaches. We'll start with Node. If you don't already have Node installed, navigate to nodejs.org and click on the big green Install button. Follow the instructions for your system, and to verify we have Node installed, we'll go to a terminal. On a Macintosh, you can hit Command Spacebar and type terminal. On a Windows machine, you can hold down the Windows button, press R, and type CMD to bring up a command interpreter. On Linux systems, the method varies widely, but if you're using Linux, you probably know how to access a terminal already. Once you get to a terminal, ensure that you've installed Node correctly by typing node-v. It should print out the Node version number. Once Node is installed, we can access it directly from the terminal. Simply type node, and we are now in Node. This is called a read eval print loop, or REPL for short. It is called that because it's going to read your input, evaluate it as JavaScript, print the result, and then start over again. For example, if I type some valid JavaScript, such as console log hello, it's going to interpret that, print the result, and finish. You'll notice that it printed hello, which is what we had logged to the console, and it also returned undefined. That's because the console log method returns undefined. If we were to enter a value or invoke a function that returns a value, we would see the value. For example, if we just type the value hello as a string, it will return the value hello as the string. Using a REPL is a great way to learn because you have immediate feedback. We'll be using it extensively through this course, but keep in mind that any code you type in a REPL will be gone when you exit the REPL. So code that you want to save, you should put in a file. Let's see how we can combine using the REPL to experiment with code we want to save. I'll exit Node by hitting Ctrl-C twice, and I'll edit a JavaScript file. I'll just call it test.js, and I'll just add a simple function. The function hello will simply log hello to the console. I go back into Node. To load my file, I simply type .load test.js, and that file will be loaded in its entirety into the current environment. Now I can invoke that function as if I had typed it directly into the REPL. Now let's look at how to access REPL in a browser. In a browser, you can access a REPL using the JavaScript console. How you get to this will vary from browser to browser. I prefer Chrome. I feel like its REPL is among the best, and so we'll be demonstrating using Chrome. On Chrome, you can type Command-Op-J on a Macintosh or Control-Shift-J on a PC, and that will take you directly to the JavaScript console. Another method is to right-click anywhere on the screen, click on Inspect Element, and that will take you to the Elements section of the JavaScript console. If you click on Console, that will take you to the JavaScript console. Just like Node, this is a REPL. If I type JavaScript, it executes it, prints the result, and returns me to the REPL. Loading JavaScript from a file with a REPL is slightly more complicated. We'll create an HTML file that contains JavaScript that will then be available in the terminal in Chrome. We'll create a file, we'll just call it test.html. The actual contents of the HTML file aren't particularly important, but I'm kind of a stickler, so I like it to look like real HTML. In the head, I'll add a script tag, And inside the script tag, I'll add a function. I'll just use the same hello function I've been using to demonstrate. And just for example purposes, I'll put a little content in my HTML. I'll save that file, and then all I have to do is double click on the file. It'll open up on my browser. I hit Command-Option-J or Control-Shift-J on a PC, and I can type hello, and it invokes my function because it's been made available in the JavaScript. This lesson is about objects as containers. The simplest way to think of objects in JavaScript is as containers or maps. Creating an object in JavaScript is very easy using JavaScript's object literal syntax. To create a new object, simply use curly brackets. We will start node. And to create an object, all I have to do is give it a name. I'll just call it O, and start with the curly brackets. I've now created an object that has no properties in it. It's just an empty object. If I type O, JavaScript will tell me that it's an empty object. If I wanted to create an object with some properties, I could have said var O name object1, for example. Now I have an object with a single property called name that has a value of object1. In JavaScript, objects can be modified at any time. For example, I can add a property to my object like so. Now my object O has two properties, name and color. I can also delete a property. Let's say I change my mind about color and I want to delete that. I can use the delete operator to delete that. That simply returns true, indicating the deletion was successful. And if I examine O now, you'll notice it no longer has color. This brings us to property access. In JavaScript, there are two ways to access a property, using the dot notation and using the square bracket notation, which is similar to accessing elements in an array. The square bracket notation is also called computed member access. Let's look at both techniques. We've already had a hint at the dot notation. If I want to get the name of the object, type o.name, it simply returns the name property. The square bracket syntax uses a string inside square brackets, so I have to put the contents in a string, o name. Keys, or properties, in objects are strings. As long as you stick to letters, numbers, except the first character, and underscores, you don't need quotes around your key names. If you need or want to store things in an object using unusual keys, you must use quotes around your keys. Let's look at a couple of examples. Name doesn't need any quotes because it uses only characters. Similarly, I could have name2. It's okay that there's a 2 in there because it doesn't start with it. If I tried to start a property with a number, JavaScript will get confused. The 3 dots indicates that it's expecting something else because the 2 came in an unexpected place in the input. So we hit Control-C to get back to our prompt. That's not to say we can't use a property name that starts with a number or any other odd character. We just have to define it as a string. Let's say we did need a property called the number 2 followed by name. We can say toName. And now if we look at our object, you'll notice that it has name, name2, and toName. Notice that toName is surrounded by quotes, indicating that this isn't a regular property name because it starts with the number 2. Using the same technique, we can give properties keys that have spaces in them. Notice that the properties with spaces in them also are surrounded by quotes. We can't access those properties with the dot notation because JavaScript would be expecting something else. For example, if I tried to access first name, JavaScript would take the space to mean that we are done and we're looking for a property called first. And again, it gets confused, so we hit Control-C to get back to our prompt. If we want to access first name, we'll have to use square bracket notation. One of the advantages of using bracket notation is that you can access properties by using a variable. For example, let's put the name of our property in a variable. I'll just use name2 for example. So now I have a string variable called prop name, and if I say prop name, it'll return object1a, which is the name2 property. That's because prop name contains the value name2. Notice the difference here. If I use a literal string, JavaScript will look for a property called prop name in the object, and no such property exists, so it returns undefined. We can also use this to construct property names using JavaScript expressions. For example, we can say name, and we can add the number 2 to that. What will happen here is JavaScript will recognize that name is a string. That means the plus indicates string catenation, and the result will be name2, and it will return object 1a, which is the property name2 in our object. The ability to use variables as property names can be incredibly powerful, and we will see in later lessons examples of this. In JavaScript, there are only 5 non-object types or primitives: undefined, null, number, string, or Boolean. Let's start Node and take a look at these different types. We will assign each type to a variable. U is undefined, N is null, num is a number, S is a string, and B is a Boolean. Each of these variables are not objects, they are primitives. Sometimes it may seem that primitives are actually objects because you can access methods on them. For example, let's take our string. We can say to uppercase, and that does something to the string and returns the uppercased version of the string. So it may appear that S is actually an object, not a string. What is really happening is that, except for undefined and null, JavaScript has object types that correspond to each primitive type. For example, if you try to reference a property of a string, what will happen is JavaScript will create a string object instance, invoke that method on it, and then immediately discard the object. So what's happening there is that S is being converted to a string object with a capital S. The string object's toUppercase method is getting called, the value is being returned, and then the object is being discarded. We can see this behavior if we try to attach a property to a primitive. For example, let's attach a property to S. So we might expect to be able to say and get the value that we put in, but we get undefined back. So what's happening here? S is being converted to a string object, string with a capital S. The isPrimitive property is being assigned to that object, and then that object is being immediately discarded. So we're essentially losing our assignment, and S goes back to being a simple primitive that has no property isPrimitive. You can create the objects that correspond to the primitive types, but it's not recommended. For example, let's say we wanted to create a string object. I'll just call it SO for string object, and I say new string and give it a value. Now you'll see SO doesn't really look like a string. That is because JavaScript has stored it as a string object. We can store properties on this now because it is a real object, but in general, you should not use primitive objects. It leads to confusing, hard to diagnose code. So generally, if you need numbers or Booleans or strings, you should stick to the literal versions of those. We can also create primitives by using the object constructor without the new keyword. So for example, I can say S equals string. Notice I am not using the new operator. And this has created a string just as if I had said S equals primitive in quotes. This can be a handy form of primitive creation if, for example, you need to coerce a string into a number. You'll notice N is a number, not a string. You can use the type of operator to determine the type of a primitive. And you can use the instance of operator to determine if something is an instance of a specific object type. Notice this. S is not an instance of the string object. As we had already discussed, S is a primitive that is different from the corresponding string object. If we created our string as we did above with a new operator, notice what happens. Type of is now listed as object, not string. And S instance of string informs us that S is actually an instance of the string object. Again, it is not advisable to create the object versions of primitives. In JavaScript, functions themselves are objects. Let's create a function and explore what this means. We'll start Node and create a simple function. call it f, and it will simply return a string, I'm a function. We can invoke f as normal, and it returns the string that we expect. Using the typeof operator, we can see that f is indeed a function. We can also use the instance of operator to tell us that f is a function. Remember that just like the literals, JavaScript has a function object with a capital F that corresponds to the function primitive. And we can see that f is indeed an instance of function. What's interesting is that f is also an instance of object. So you can see that f is both an object and a function and has properties of both. Just so you don't think that instance of always returns true, let's see if f is an instance of a string. And it is not, as we expected. We can verify that this function behaves as an object by giving it a property. We see f now has a property foo that we can access as if it were a normal object. In a bizarre twist, we can also give a function property. We've created a function called metafunction on f that returns a string I'm a function on a function. If we simply say f metafunction, it will just tell us, yes, that's a function. But if we invoke it, just as if we would invoke any function, we'll see that it operates just like a regular function. So now we can invoke f, and we can invoke a metafunction on f. In practice, this property of functions is seldom used, but it can be very useful in certain situations. Function properties of objects are special in JavaScript. In object-oriented lingo, a function that's a property of an object is called a method. Let's create a method by assigning a function to an object. We'll start up Node, and we'll be using the shopping cart example we'll be using throughout these lessons, as if we were creating an online shopping cart. We'll create an object called cart, and we'll give it a subtotal function. Right now, we'll just return 0 as if the shopping cart is empty. We can now call cart.subtotal, but there's nothing special about this so far. It simply returns 0, and we could have accomplished that with a regular function that's not attached to an object. Looks like I made a typo. Let's try that again. And return 0 as expected. What's special about methods is that they bind a special variable in JavaScript called this. This refers to the object the method was called on. Let's modify our example to have a customer name, which is logged to the console when subtotal is called as if we were trying to debug our program. We'll simply recreate our cart, give it a customer name, and we'll give it our subtotal function. This time, we'll log the customer that the subtotal method is being called against. Notice that I use the keyword this to get the customer. If I simply called customer without the this, JavaScript would assume we're talking about a global variable. Sometimes you'll hear this referred to as there being no explicit this in JavaScript. And then we'll simply return 0 as we have been before. Now let's try to invoke that function. 0 is returned, as it has been before, but now subtotal called for Judy is being logged to the console. Let's create a different cart and use the same function and see what happens. Give this a new customer name, and we'll also give it a subtotal function, but instead of typing in our subtotal function all over again, let's just reference the one we already have. Notice that I don't provide parentheses. That's because I don't want to actually invoke the function here. I want to get a reference to the function and use that in cart2. Now I can call this cart subtotal. Looks like I made another typo. I can get the subtotal for Judy's cart, and I can get the subtotal for Greg's cart. The reason it's able to distinguish these two is because it knows which object I'm calling it against. When I call it against Judy's cart, this.customer refers to Judy, and when I call it against Greg's cart, this.customer refers to Greg. It's important to understand that the binding of this is dependent on how the function is invoked. For example, let's create a reference to the subtotal function that's not associated with any object. Now, subtotal alone, cart.subtotal, and cart2.subtotal are all the same function, or more specifically, they're references to the same function. We can verify that by using the triple equal operator. And we can also see that cart.subtotal is the same as cart2.subtotal. Looks like I made another typo. So I can see that those are all actually the same functions. The functions behave differently, though, depending on how I invoke them. If I invoke the function against the first cart, it prints the cart for Judy. Cart 2 prints the subtotal for Greg. And subtotal alone says subtotal called for undefined. That's because subtotal alone wasn't invoked against an object. It's true that we copied that from the cart subtotal, but when we did that, we lost the binding between the object and the function, so JavaScript doesn't know how to associate the two anymore. For subtotal alone, the this variable does exist. It's undefined, but it exists. If you invoke a function that's not specifically on an object, it will use the root object or the global object as this. So for example, we could fool JavaScript by creating a global customer variable. And now when I invoke subtotal alone, we'll see that it's referring to that global variable. This isn't advisable. It's not a very object-oriented way to operate, and it's exploiting a consequence of the way JavaScript invokes functions. It can sometimes come in handy, but I don't recommend using it as a normal course of action. The rule of thumb is if you use this in a function, that function should be invoked as a method. We will be covering the this keyword in much greater detail in later chapters. We invoke a function or a method by placing parentheses with optional arguments directly after a reference to the function. A method is simply a property of an object and can be accessed just like a regular property, either with a period or with square bracket notation. Once you have the function reference, you can invoke it by supplying parentheses. Let's start up Node and take a look at how this works. We'll start by creating a cart object with a function that returns a subtotal. Let's return something more interesting than 0 for now. Let's say there's $35 worth of merchandise in the cart. We'll be replacing this with some actual functioning code later, but for now, we're just going to use a number. If I simply access subtotal without invoking it, it simply returns a function reference. So if I say cart subtotal, Node tells me that yes, that is indeed a function. To invoke it, I simply supply the parentheses, and the function is invoked and my value is returned. We can also access the method using square brackets. So I can say cart subtotal, and that's a function, and again, I can invoke the function. There's really no difference at all between those two methods. The handy aspect of using square brackets, which are also called computed property access, is that you can invoke methods dynamically. Let's consider an example. We'll create a slightly more sophisticated cart object. We'll give this one a tax rate. We'll arbitrarily assign it a value of 3.5%. We'll give it a subtotal function, which does not include taxes. Returns the $35 worth of merchandise that's in the cart. And then we'll give it a total function, which returns the subtotal plus the subtotal times the tax rate. Note that I have to use the this keyword here. If I omitted the this keyword, then JavaScript would assume we were referring to global variables such as subtotal and tax rate. Looks like I forgot a parenthesis, so let's go back and add that because we want to invoke the subtotal function. So now if we take our cart and we invoke the subtotal method, it returns 35 as expected. And if we invoke the total method, it returns 36.225, which is the value of the items in our cart plus the tax rate. Now we've constructed this example so we can demonstrate the usefulness of accessing methods with the bracket notation. Let's say we wanted to dynamically access either total or subtotal depending where we were in a checkout process. At the very final step, we would want to use total, and all the steps before we would want to use subtotal. Let's say at the final step we have a variable called final step, and that's true. And we can dynamically figure out which function name we want to use. So we'll just create a variable called method name. And if the final step is true, we'll use total. And if the final step isn't, if we're not at the final step, we'll use subtotal. So since final step is true, method name should simply be a string referring to total. Now, if we call cart with square brackets using the method name, which is total, specifically it's returning total, not subtotal. So if we invoke it, we should see the total with tax. If we change method name to be subtotal, and we re-invoke that expression, you see we have the subtotal. In this way, we can very easily dynamically pick out methods and properties of an object using the square bracket notation. In JavaScript, you have to take extra care when you're using the this keyword in functions inside functions, also called inner functions. This is widely considered an unfortunate flaw in JavaScript and will likely change in future versions, but you should be aware of the issue. We'll start up Node and create a cart object. We'll create a subtotal function, which is just going to return a fixed value for now, and a total function that's going to compute sales tax and provide the total. For convenience, we're going to encapsulate the code that calculates sales tax into its own function. This is called an inner function. We'll just call it getTax, and it will simply take the subtotal and multiply it times the tax rate. Now that we have that function handy, the total function becomes very easy. We simply return the subtotal times the tax, which is handily encapsulated in the getTax function. This all looks pretty straightforward. We've encapsulated the functionality that computes tax into a helper function, and we're using that inside our method. However, this will return unexpected results. Let's give it a try. Cart subtotal works as expected. The cart total returns an error. Object has no method subtotal. In JavaScript, variables normally have function scope, so a variable declared in the total function will be available to inner functions, such as getTax. Given that, it seems like this should work. This is a variable that's available inside total, so it seems like it should be available inside getTax as well. However, this is a special case. This is always bound according to how the function is invoked. So in this case, this is not cart inside getTax, but the global object instead. Since the global object has no method subtotal and no property tax rate, you get an error because JavaScript doesn't know how to invoke the subtotal function. In the next lesson, we'll see a common way to deal with this issue. This lesson is about the this and that variables. We've already seen that calling functions from within methods can cause problems. Let's consider an example that expresses this issue. Imagine that all of the items in our shopping cart can have a discount applied. Let's create a function that applies discounts to all of the items within a specific category. I've created a cart file for you, cart.js, in your chapter 3 directory. It has items, a grocery cart, an apple, some corn. Each item has a category, a price, and a quantity. And then there's a list of discounts by category. There's a 10% discount on produce and a 20% discount on canned goods. Let's write a function that applies discounts to all the items in the cart. Call it applyDiscounts. And we'll use the forEach method of array to iterate over the items. We'll first get the discount for this item's category by using this discounts in the item that the category belongs to. If there is no discount for this category, the discount variable will be undefined. Also, it's possible for there to be a discount variable that has a value of 0, which we would also want to skip over. So let's skip over anything that's falsy. And then we'll apply the discount. Instead of modifying the item's price, I'm going to create a new property called discount. And that's simply going to be the item's price times the discount. Let's save this file and open it in Node. We load it in Node by typing .load cart.js. There, the file has been loaded into Node. We see the items in our cart and the discounts and the discount function. Let's go ahead and call applyDiscounts and see what happens. Looks like we have an issue. Node is telling us that it cannot read the property produce of undefined. Produce is an item category, so it looks like when we try to get the discount, we have an issue. Let's go back to our source file and see what's going on. The problem is here on line 14. We're calling this.discount and trying to get the discount for the item's category. The problem is, notice that we're inside an inner function. On line 13, we're creating an anonymous function, and the context is different. In particular, this is not bound to the object's context. As it turns out, this is bound to the global context in this case, and the global object doesn't have a discounts array. There are several ways to get around this problem, but the one we'll be using in this lesson is using a helper variable, which we'll call that. In the beginning of this method, we'll create a variable called that, which simply refers to this. So that and this are references to the same object. The difference is that the variable that is not considered special in any way by JavaScript. So the normal rules of function scoping apply. And inside the anonymous function, defined now on line 14, that doesn't hold any special meaning, and it points to the object we're interested in, i.e., what was known as this. So let's change this reference this to that. Now let's save this, open Node, load our file again, and let's try it again. We don't get an error this time, and our function isn't returning anything, so we get undefined back as expected. Let's look at the items in our cart now. We now see that apple has a discount applied, and canned corn has a discount applied, and lettuce has a discount applied, but milk doesn't because we didn't have a discount category for dairy. So now the function is working as expected. I personally dislike using that as a variable name. I feel that it's too generic and can be very confusing keeping track of what that is as you get deeper into the code. However, I wanted to start with a variable called that because it's quite common, and I didn't want you to be confused when you saw it in other people's code or other explanations. Another common variable name you'll see is self. This is slightly better, as self really seems like the same thing as this, but I still don't care for self, as it seems redundant to have variables called this and self. If you're going to save the value of this, why not use a variable name that expresses what this actually is? This is my preferred technique. In this case, this is really an instance of a shopping cart, so let's just call it cart. Let's go back and modify our function again. Instead of calling our variable that stores this that, we'll call it cart, which is really what it is. It happens to be this cart, but it's still a cart. And here inside the anonymous function in the for each, we can call cart discount. We haven't changed anything fundamental, we've just renamed a variable, but it makes the program easier to read. Let's load our program again and make sure we didn't break anything. We invoke apply discounts, it returns undefined. We look at our items, and we see the discounts have been applied appropriately. Functionally, nothing has changed, but now the code is easier to read, and it's easier to understand what's going on. In the highly asynchronous world of JavaScript, callbacks are a common way to handle asynchronous functionality. Common examples of asynchronous functionality are user events, such as the user clicking on something, or timed events. Let's imagine a made-up scenario of when we might need to use a callback. Imagine that we want to reward our customers by putting something free in their cart if they've been shopping for a long time, which hopefully means they've been putting more items in the cart. Let's imagine that our cart has a function called add freebie that adds a candy bar to the cart if the user has been using the cart for more than 2 minutes. Let's go ahead and write our add freebie method. I've prepared a sample cart implementation for you called cart2.js, and you'll see that it's just a simple cart with some items already in it. We'll go ahead and create a function called add freebie, and we're going to use a console log, which will make it a little easier to see what's going on. And then we're just going to add a candy bar to the cart. And that's all there is to it. Now let's create a timer to automatically add the candy bar after 2 minutes. Because I don't really want to wait 2 minutes, for testing purposes, I'll use 2 seconds instead. After our cart object definition, I'll call setTimeout. I'll give it the add freebie method as the function I want to invoke after the time, and I'll give it a time of 2000 milliseconds or 2 seconds. Let's go ahead and try that and see what happens. Save that file, start Node, load cart2.js, and once we do, the cart will load, there will be a 2-second pause, and then it should call add freebie. Let's see what happens. That loads okay, the set timeout goes, and then after 2 seconds, we get an error. Cannot call the method push of undefined. Let's take a look at our function and see what's going on. Since Node told us that it couldn't find a method push of undefined, that tells us that the problem is here on line 10. It indicates that items is undefined. This should be familiar now. This is probably not what we expect it to be. We've written this as if we expect this to be the cart object. But you'll notice that we invoke it in setTimeout. We simply pass setTimeout the function. We don't actually invoke it. When setTimeout invokes a function, it doesn't invoke it as a method of cart because it doesn't know about cart. All it knows is being passed a function. And therefore, the binding to this is lost, and we get the error we saw. There are a couple of ways to solve this. One very easy way is to just create an anonymous function and wrap our method invocation inside it. Let's try that. Instead of passing addFreebie directly to setTimeout, let's create an anonymous function. And inside that anonymous function, we can call cart addFreebie. Notice that we do actually invoke addFreebie now, indicated by the parentheses, instead of simply passing it to setTimeout. In this way, Node will know to invoke addFreebie as a method because it's being invoked against the cart object, and this will be bound correctly. Let's go ahead and load it up and see if this works. Wait 2 seconds, and we get our console log that the freebie was added. Let's look at the items in our cart, and sure enough, the last item is a free candy bar. Later on, we'll see some more sophisticated techniques for dealing with this problem. For now, you should avoid using methods as callback functions, as this is a common problem you can run into. At this point, we're pretty familiar with function invocation. We know that all we have to do is add parentheses to something that's a function, and it will invoke the function. But that's not the only way to invoke a function in JavaScript. You can also invoke a function with two special methods called call and apply. Let's look at how we might invoke a function with these other functions. Let's start with a simple function that returns the sum of the squares of its two arguments. We'll start Node, and we'll create a function sqsum, which takes two arguments, and we're going to return the sum of the squares. So we'll use math.pow, which raises a number to a power. We'll raise a to the second power, and we'll add it to b raised to the second power. So we see we can invoke the function in the normal manner, and we get the sum of the squares of 2 and 3. We can also invoke it by calling its call method. Let's give that a try. sqsum.call. The first argument will be null. We'll be talking more about that later. And then we just pass in 2 and 3. The result, of course, is the same as if we had called it normally. However, there's more that we can do with call. Let's set it aside for now, though, and try the same thing with apply. sqsum.apply. And again, the first parameter will be null. And then the second parameter will be different. We'll pass in 2 and 3 as an array, and it's as if we had passed them in a list. So it looks almost the same, but passing the arguments as an array can come in handy when you have things that are already an array, and you want to invoke a function with the elements of the array as arguments. So what about that first parameter? That first parameter for call and apply specifies what to bind to the this variable. This ability allows us a lot of flexibility in JavaScript that we don't have in other object-oriented languages. And now that we know this, we start to see that JavaScript truly is a language that's about functions first and methods second. Let's create a couple of simple objects that have methods and play around with call and apply. We'll create an object called hello. That has a name. We'll just call it welcomebot. And it has a method called speak. Takes a single argument indicating who is being spoken to. And we'll just return a little message. Similarly, we'll create an object called goodbye. We'll call this farewellbot, and we'll give it a speak method. So now we have two objects, hello and goodbye. Let's give them a shot. We can call hello speak. I'll put my name in there, and we get back what we expected. Welcomebot says, welcome Ethan. And similarly, we can say goodbye, speak, and farewellbot says goodbye, Ethan. Now let's try the same thing using call. Hello, speak, call, null. I'll pass in my name. Now something interesting has happened. You'll see it says undefined says welcome, Ethan. That's because we passed null in as the this object, and we've lost our binding to the hello object. Speak is just being treated as a function that's being invoked without any context. We can fix this, of course, by passing hello back in as the this object. And then we get the same thing as if we'd called hello on speak without call. So far, all we've really done is to recreate normal function invocation, which really is just making our code longer and more confusing. What if we did this, though? Hello, speak, call, and this time we're going to pass in goodbye, as the this object. Now I have my farewell bot welcoming me. You start to see the utility of being able to call and apply. You can invoke methods from one object on another object as if it belonged to it. Of course, this works exactly the same with apply, it's just we pass our arguments in as an array instead of in a list like normal function invocation. Let's give it a try. We'll call hello, speak, apply. We'll make the farewell bot do it, so we can see that we're changing our this binding, and we'll pass my name in as an array. Similarly, we can say goodbye, speak, apply. We can use the hello bot, pass in my name as an array, and we have the welcome bot doing the goodbyes. You might be wondering what the point of this is. Certainly, in this contrived example, we've really only served to create confusion. However, the ability to modify the this object can be very useful in certain circumstances. For example, it allows you to pass a function around as a variable and still invoke it as if it were a method. Let's look at an example of how that might come in handy. Let's say we just wanted to pass the speak method around and use it just as a function. So we'll create a variable called speak, and we'll pull it off of the hello bot. So if we look at it, speak is simply a function that we can invoke. If I say speak Ethan, however, it's going to say undefined says welcome Ethan. That's because there is no more this binding. Even though we pulled the speak method from the hello object, once we saved it in a variable, we lost its binding to the object it came from. Fortunately, we can use call to get our functionality back. Speak, call. We'll call it with the hello bot. Give it my name. And you can see all is well again. We've managed to invoke the function against the hello object, even though we only have a variable pointing to the function instead of calling it against an object. We can also invoke functions as methods of objects we create right on the spot. For example, let's take hello, speak, call, and instead of passing in an actual object we have lying around, let's just create a new object. We'll call it another greeting bot. And again, I'll pass in my name. Another greeting bot says, welcome Ethan. So you start to see the flexibility of being able to invoke functions with call and apply. You can create objects on the fly and invoke methods from other objects. One common use of JavaScript's ability to change what this is bound to is doing the same thing to a bunch of objects. Let's say we want to number all of our robots. We'll create a function called numberRobots. And all it will do is give the current robot a number. So we'll say this robot equals n. It might strike it odd to you that we're using this in a function as opposed to a method. And in any other object-oriented language, that would be odd. But because JavaScript is different and you can change what this points to, we can make it work out. Let's create an array of our robots. We only have two of them, the hello bot and the goodbye bot. And now we can create a for loop. We'll call numberRobot using the call method. And we'll call robots I with the number. And that will invoke the numberRobots function as if it were a method on each robot. So now if we look at our hello robot, we see it's robot 0. And if we look at our goodbye robot, we'll see it's robot 1. Essentially, we've created a method without attaching it to any object. Some of JavaScript's built-in functions even allow you to specify this argument. Internally, these functions use call or apply to invoke the function with that this argument. For example, array prototype for each allows you to specify a this argument. Imagine we have an object that's called a robot registry that we want to use to register all of our robots. Let's go ahead and create that object. We'll call it robot registry, and it will have a list of robots. It'll have a method called addRobot, which simply takes a robot, which I'll call R, and pushes it onto the array. So now we have a robot registry, and we can call for each and invoke that function. Now if we just call it this way, robot registry addRobot, it will invoke addRobot as if it were a function, not a method. And then this variable would not be bound, so this would not have an array called robots and the push would fail. Fortunately, for each allows us to specify what to use as this. So we'll just use robot registry as this, And now if we look at our robot registry and its list of robots, we'll see that all of our robots are in there. In this way, we're able to invoke add robot for each robot in our array, and then this variable will be bound to robot registry. So all the robots will end up in the robot registry. Note that we are using a method as a callback, which we have seen before is problematic. But in this instance, we are explicitly telling for each what we want to bind this to, so it avoids the problem. Using call and apply can be a very handy trick, but be careful with it. It can also create confusing, hard to understand code. Think carefully before you use it. Bind is another way to deal with the problem of invoking methods when you can't call them against the object they belong to right away. Bind permanently binds a specific this value to a function, allowing the function always to be invoked as a method, no matter where or how it's invoked. Let's start up Node, and we'll create a couple of objects, hello and goodbye. And hello will have a name, we'll call it greetingbot, and it will have a speak method that emits its name, says hello to the subject, and then we'll also have a goodbye object. It's almost identical. We'll call it farewellbot. Similarly, we'll go to speak function. Normally, if we save a reference to a method and then invoke it, it won't be invoked in the context of the original object. For example, if we say speak equals hello speak, the variable speak no longer contains the context of the hello object. So if we simply try to call speak, and I put my name, it says undefined, it says hello Ethan, because it doesn't have a binding to the hello object. That's where bind comes in. We can call bind to get it to always be bound to the original object. For example, I can say speak equals hello, speak, bind. I'm going to bind it to the hello object. We can bind it to any object we want, but in this case, we simply want to bind it to the hello object that it came from. Now if I call speak, and I give it my name, it will say greetingbot says hello Ethan. Note that even if we use call or apply, it will still be bound to the original object. For example, if I call speak, call, and I try to call it against the goodbye bot, hoping to see farewellbot says hello, and I give it my name, it still says greetingbot says hello Ethan. That's because once a function has been bound, it cannot be modified, even by call or apply. So you could say that binding takes precedence over call and apply. Bind can be especially useful with callbacks. Let's say that we want a delay before saying goodbye. If we don't bind it, then we will lose the context we were looking for. For example, set timeout, and we'll say hello, speak, and we'll give it a delay of 3 seconds. We'll wait 3 seconds, and it says undefined, says hello, undefined. Now we can pass a variable to set timeout. That's the last parameter. So I can give it my name, wait 3 seconds, and now at least it says hello Ethan, but it still says undefined. That's because it's lost the binding to the context it was invoked from. We can solve this problem by using bind. Set timeout, hello, speak, bind, and we're going to bind it to the hello object. We'll give it a timeout of 3 seconds, and we'll give it my name. We'll invoke that, wait 3 seconds, and now greetingbot says hello Ethan. So this is a great way to use methods with timeouts or other asynchronous functions. You should be careful with bind, as a bound function will not allow its this argument to be modified with call or apply. If you're using call or apply a lot, and you expect them to always modify the this argument, you will want to avoid using bind. This lesson is about function scope in JavaScript. How variables are scoped generally isn't considered germane to object-oriented programming. But if you're unfamiliar with scoping in JavaScript, it can be a barrier to understanding important object-oriented concepts. So this lesson will be a brief review of scoping in JavaScript. In JavaScript, variables have function scope, which is a departure from most other languages in the C family, which have block scope. I'll fire up Node, and I'll create a function called scopeTest. Inside the function, I'll have an if statement. I'll just say if true, which will always evaluate the body. And inside the body, I'll create a variable. I'll just call it foo And then outside of the if statement, I'll log foo. Now, in a language like C# or C++, this would fail to compile because foo is defined inside the block of the if statement. But in JavaScript, there's function scope. So foo is defined within the function scope test, therefore it is available throughout the entire function. We can verify this by running scope test. Sure enough, it prints the value of foo. The way JavaScript manages function level scope is a process called hoisting. Hoisting will trip up many a beginner, so let's discuss how hoisting works. In JavaScript, variable declarations are hoisted to the top of the function, but not variable assignments. Let's get out of Node and go into an editor so we can see this a little clearer. I'll just call it test.js. This is a throwaway file. I'll rewrite my scope test. Now, when JavaScript goes to evaluate this, the first thing it does is it hoists all the variable declarations. Not assignments, just declarations. So let's rewrite this function the way JavaScript sees it. JavaScript will parse through here and see there's a variable declaration on line 3. The variable foo is being declared. So JavaScript will take that declaration and it will hoist it to the top of the function. Notice that the assignment isn't hoisted, just the declaration. Then we can remove the var from what is now line 4 because the declaration is now on line 2. This should make it clear how foo is available to the console log on line 6, even though it is declared inside the if statement. JavaScript actually hoists the declaration to the function level scope. One way that hoisting often trips people up is when masking variables in outer scopes. Let's consider an example that demonstrates this. I'll leave my function scope test. I'll create a message. Say the message is boring number because we're going to be looking at numbers. And then I'm just going to iterate over through some numbers in an array. I'll use JavaScript's built-in for each method. And so function will get called for each element in this array, the anonymous function. Inside the anonymous function, I check to see if the number is less than 3 arbitrarily. And if it is, it's a boring number, and I return a message to that effect. If it isn't a boring number, i.e. it's 3 or more, I create a new message. How we expect this function to work is that it will print 1 boring number, 2 boring number, 3 exciting number, 4 exciting number, and 5 exciting number. That's what we expect the way we've written it, but let's see what happens if we actually run it. Enter Node. I'll load my file, .load test.js, and then I'll call my function. You'll see that we don't see what we expect. We get undefined for 1 and 2. Let's edit the file again and see what's going on. The problem is that we have an anonymous function declared on line 3. So all of the variables inside that function have function scope. So let's employ the rules of hoisting and see how JavaScript would rewrite this. Of course, it'll see a variable declaration here on line 2, and it will hoist that, although that's not going to affect things much. So MSG has been hoisted to the top of the function, and MSG is still boring number. Here we have another function on line 4 now, and inside that function, JavaScript will also hoist variables. So we'll scan this function, it will recognize that there's a variable declaration here on line 6, and it will hoist that to the top of the function. Now it's a little more clear why the first 2 numbers are returning undefined. Because on line 5, we declare a new variable that's going to mask the variable in the outer scope, and by default, new variables have a value of undefined. So the first 2 numbers return undefined, whereas numbers after 3, MSG is getting an assignment. JavaScript ES6, or Harmony, introduces a different way to declare variables, using the let keyword instead of var. Let declares variables in block scope instead of function scope, and it is expected that eventually let will replace var altogether. For example, let's delete the contents of scope tests and see how var might work. Again, we'll have an if statement. Inside the if statement, we'll use let instead of var. If we were to execute this, JavaScript would tell us that foo is undefined on line 7. That's because let is informing JavaScript that the variable foo is block scope, and it will exist only in the block made up by the if body. You'll notice the use strict directive. This tells JavaScript that it should use strict language parsing, and currently, if you want to use let in JavaScript engines that support Harmony, you'll have to use useStrict. Using useStrict is a good idea, and I recommend it always. Another thing that trips up newcomers to JavaScript is the creation of implicit global variables. If you forget to declare a variable within a function, you are creating an implicit global. Global variables are generally considered to be bad practice. They create side effects that are hard to track down, and it leads to fragile, unmaintainable code. Let's look at an example of implicit globals. I'll exit my editor, and I'll go into Node. If I just type foo, JavaScript will tell us that there is no foo defined, which is expected. We haven't defined anything of the sort. Let's create a function. Again, we'll call it scope test. And inside the function, I'll just set foo equals 5. Notice I didn't say var or let, just foo equals 5. If I call scope test, I would expect foo to be defined and live entirely within the scope of the function scope test. But that's not actually what happens. If I type foo now, I'll see that it has a value of 5. That's because if I omit the var keyword, JavaScript assumes that I want to create a global variable. This is generally a terrible idea and is widely considered one of the weaknesses of JavaScript. One way you can prevent doing this accidentally is to always use useStrict. Let's see what happens if we redefine our function with useStrict. On the first line, I say useStrict, and then I say foo equals 5, close my function. Now I'll see what happens when I call my function. Of course, we still had our foo around from earlier, so let's delete that and try it again. Now if we look at foo, it's undefined on our scope test, and you'll see now there's a reference area. Foo is not defined. It doesn't recognize it because it knows that it's in the global scope. Sometimes you do want to mutate the global scope. It's generally not recommended, but sometimes it is an expedient way to get things done. If you really do want to modify a global variable, I recommend making it explicit by naming the global object. In a browser, the global object is window, and in Node, it's global. Since we're in Node, let's rewrite our function declaring an explicit global variable. I say global, and I'll just call this global foo equals 5, and now I'll run scope test, and we'll see that global foo is now in the global scope. The advantage of this approach, even though we could have simply omitted the global dot, is that it's very clear that a global variable is being created. If you omit it, it probably means that you just made a mistake and left off the var or let, which is a bad idea. So I always recommend specifying the global scope if you really want to mutate the global scope. One aspect of object-oriented programming that JavaScript does not natively support is data hiding. In most object-oriented languages, you can declare a method or a member variable to be restricted somehow, such as private or protected. Although JavaScript does not allow you to mark object properties as private, data hiding is often accomplished in JavaScript through the use of closures. In addition to being useful in data hiding, understanding closures is essential to understanding how most modern JavaScript code functions. Whenever you're inside a function, you're inside a closure. And as long as that closure exists, variables within it exist. Let's look at an example. I'll start up Node, and I'll create a function. I'll just call it closure. There's nothing special about that name, it's just what we're talking about. I'll create a variable called inside closure, and I'll give it a value. I'm going to return a function from this function. This may seem a little odd, but we'll understand why in a minute. And all the inner function is going to do is call console log inside closure. This will end the return function, this will end the closure. Now I have a function closure that in turn returns another function. Let's go ahead and invoke it. You'll see that Node is telling me that it returns a function. That doesn't do much good, of course, unless I actually save the value of the function. So let's go ahead and save it. I'll just call it fn for function, and I'll invoke closure. So now if I look at fn, it's a function, and it can be invoked as a function just by adding parentheses. And you can see it returns the console log inside closure. Now, what's interesting about this is normally inside a function, you think of variables lasting for the scope of the function and then disappearing. For example, if we didn't do anything special inside closure, the variable inside closure would be released after closure finished executing. But since it returns a function that accesses that variable, JavaScript knows it has to keep it around because it doesn't know when that function might be called. The variable is the same every time fn is called. If I call fn again, you'll see it still has the same variable. In a way, we've captured a value inside this closure, and JavaScript will keep it until there's nothing left pointing at it. In addition to the fact that the variable inside closure is living longer than you expect, we also have another consequence of the closure. We can't actually get at the variable inside closure. We can see its value if we call the function that was returned from the closure function, but we can't modify it. In essence, that variable has been hidden from us by the closure. We can leverage this to create private variables in objects. Let's use this concept to create a function that counts the number of times it's been invoked. I'll first create a generator function. I'll call it getCounter function, and I'll create a variable to hold a count. I'll just call it count equals 0. And then my function is going to return another function. I'm going to give it an arg so I can do more things with it. In this case, I'll allow you to reset the counter. So if arg equals the string reset, then I'll set the count to 0, and I'll console log counter reset. If the arg isn't reset, I'll simply log the new count. This closes our enter function. This closes getCounter function. Now we can generate a function that can count how many times it's been invoked. If I call fn, you can see it's been called 1 time. And if I call it again, it's been called twice. And if I call it a 3rd time, it says it's been called 3 times. What's interesting about that is the outside world can't get at the count variable, so we can't mess it up or interfere with it. fn will always accurately report the number of times it's been called. Of course, we did build in a reset functionality, and we can reset the counter. And now if we type fn, it's been called 1 time, and so on and so forth. So we can see in this example that by using a closure, we can create variables that can only be accessed by what the closure chooses to expose to the outside world. We can use this in object-oriented programming to create a sort of hidden private variable. If you're new to asynchronous programming, certain things can really trip you up. Let's look at an example and see how closures and IIFES can fix the problem. Let's say that we want to do a 5-second countdown. We might start off by trying something like this. Create a file called countdown.js. I'll have a function called countdown. And I'll start with 5. And while I is greater than 0, which will make it stop at 1, I'll decrement the value of I. And I'll call set timeout. On the timeout, I'll log the value of I and do that every 1,000 milliseconds, which is 1 second. So this looks pretty reasonable. I'm creating a loop from 5 down to 1. I'm calling set timeout after a second and logging it to the console. Let's load it up in Node and see what happens. We've loaded our countdown function, so let's invoke it. Well, that's not the result we expected. After a second, it prints 0 5 times. Let's see what's going on here. The problem is that set timeout basically creates an asynchronous event. You're basically telling JavaScript to defer what's being called in the anonymous function on line 4 to a later time. In this case, 1,000 milliseconds in the future. So when you invoke countdown, JavaScript executes line 2, line 3, then line 4, but it doesn't execute what's inside the anonymous function. It's saving that for later. Then it goes back to line 3, then line 4 again, then line 3, then line 4, and so on, 5 times. And then finally line 5 and line 6, and the function is done. Then, a second later, all of the anonymous functions get invoked. The problem is, I is inside the closure formed by the countdown function. Inside the for loop, I isn't changing, therefore the I that's being referenced inside the setTimeout anonymous function is the same I that's in countdown. And when countdown finishes executing, the value of I will be 0. That's why when the anonymous functions inside setTimeout get around to executing, I will be 0 for them all because they're all referring to the same variable that happens to have a value of 0. We can fix this problem with a closure or an IIFE. I'm going to go ahead and type it out, and then we're going to talk about the syntax, which will seem odd if you've never seen it before. So this definitely looks a little odd, but let's break down what's happening. Here on line 4, we look at it from the inside. We're creating a function. This anonymous function stretches here from line 4 to line 6. By putting it inside the parentheses, we're forcing JavaScript to execute that function declaration. What the parentheses evaluates to is a function. And of course, we know we can invoke a function by putting parentheses after it. So we put parentheses after it, and we pass in the value of I. This function takes one formal argument that we've called ICaptured. We can call it whatever we want. We could even call it I, which would then mask the value of I from the outer scope. The unique thing is that ICaptured is now inside the closure created by this anonymous function. So it's a different variable than I that is created by the closure of the countdown function. So when setTimeout eventually calls, it has its own copy of I, which is stored in ICaptured. And it's essentially captured the value of I at that specific moment in time in a different closure. So let's load this function into Node and see what happens. We've loaded our function. Now let's invoke it. After a second, it prints out 5, 4, 3, 2, 1. Now there's still a problem here, of course. We had kind of expected to see 5, followed by a pause of a second, followed by 4, followed by a pause of a second, followed by 3, and so on. Instead, we waited 1 second, and all of the numbers are emitted at once. Let's see what's going on here. When JavaScript invokes this for loop happens in an instant, less than a millisecond, no doubt. Each time the loop executes, it calls setTimeout with a value 1 second in the future. The problem is, it's all essentially the same second. For example, if this were a really slow computer and the loop executed once every millisecond, then the first function would get called exactly 1 second later. The second function would get called 1 second and 1 millisecond later. The third function would get called 1 second and 2 milliseconds later. And to the naked eye, it would appear that they're all getting called at once after 1 second. There are a couple of ways we can solve this problem. One way would be to chain the setTimeouts. So the first setTimeout calls setTimeout for the next number, and then the next number calls setTimeout for the following number, and so on and so forth. That's a slightly more sophisticated implementation, though, that we don't have time for. Fortunately, there's an easier approach we can take to this. Instead of specifying a timeout of 1,000 for the first one and 1,000 for the second one, we can specify a timeout of 1,000, 2,000, 3,000, 4,000, and 5,000. Fortunately, we have the number of seconds captured in ICaptured. So really, we can say ICaptured and multiply it times 1,000. Now we're counting backwards, so we want to start at 0. So the first time this runs, it'll be 5 minus 5, which will be 0. So the first set time will get executed immediately. And then 1 second later, ICaptured will be 1. So it'll be 5 minus 4 times 1,000, which will be 1,000. And then 5 minus 3 times 1,000, which will be 2. And so these will execute every second. Let's give this a try and see what happens. We see it prints the countdown that we expected. One last thing I'd like to point out before we move on. In line 5, at the end, we subtract ICaptured from 5 to get the number of seconds we should wait before invoking this function. Note that we could have actually used I here instead of ICaptured. In this case, it doesn't matter because setTimeout is getting invoked inside the context of countdown. It's only the anonymous function that's getting passed as the first argument whose execution is deferred until later. When setTimeout is called, the second argument, if we used I, would be what we expect it to be. Whereas if we use it inside the anonymous function, it would get the value that I eventually becomes because the execution is being deferred. So in this one example, we can see very neatly the use of a variable that is deferred versus the use of a variable that is executed immediately. The concept of closures and their uses can take a while to get used to, but the concept is very important in JavaScript, and they're incredibly useful. In most object-oriented languages, there's a distinction between a class and an object. A class is more generic. It represents a type of object. For example, car might be a type of object, or a class, and my car is an instance of class car. Classes allow you to describe common structure and behavior for related objects. JavaScript, in contrast, doesn't have a formal concept of classes. However, the idea of classes is useful, and JavaScript does provide a mechanism for providing some of the same functionality that classes provide. JavaScript provides a mechanism whereby a function can create an object instance that has common functionality and structure. This is very similar to the concept of a constructor method in other object-oriented languages. Let's take a look at a constructor function that will create a new shopping cart instance. I'll create a file called cart.js, and I'll create a function called cart. Give the cart a name. I'll just call it Granny's Grocery. Give it some items, currently empty. There are a couple of things to note about this. First, you'll notice we name the function with a capital C. This is not required, but it is a convention borrowed from other languages. Class names start with a capital letter, and all other identifiers, like functions, methods, variables, and properties, start with a lowercase letter. While this is only convention, I strongly discourage you from straying from it. The other thing you'll notice is that we're using this, even though this function doesn't appear to be a method. We know that we could bind this using call, apply, or bind, but JavaScript provides a special keyword designed to work with this kind of function, new. The new operator is designed to create a new instance of an object using a construction function. Let's see it in action. I'll go ahead and save this file. I'll start up Node, load cart.js, and I'll create a new cart using the new operator. I simply say var cart equals new cart. Note two things. First, we called our variable instance cart with a lowercase letter. Not only does it distinguish it from the constructor function cart with a capital C, it follows our convention of everything but object constructors starting with a lowercase letter. Also note that we supply parentheses as if we were invoking cart like a normal function. While it is invoked as a function, the new operator tells JavaScript to treat this invocation as an object creation. The cart variable will get assigned the value of a new object that the cart container generates. Let's take a look. You can see cart has a property called store that contains the name of the cart and contains an array of items, which is currently empty. Let's add an item to the cart. We can see that our cart now contains that item. Now let's create a different cart. I'll just call it cart2. And let's see what it contains. Nothing, because it's unrelated to cart1. You'll notice that cart and cart2 are now separate instances with separate data. In other words, each time the constructor function was called, a new store and items property got assigned to the newly generated cart instance. Note that you'll get into trouble if you call the cart constructor without the new operator. For example, if I say cart3 equals cart, and I omit the new operator, and then we examine cart3, we'll notice that's undefined, which is not what we wanted, and even worse, there's now a global variable called store and a global variable called items, which should have gone into cart3. This is because if you omit the new operator, the constructor function will execute in the global scope. We can see that not only is cart3 undefined, we have leaked variables into the global space, which is definitely not what we wanted. This is why adhering to the convention of object constructors starting with a capital letter is so important. It allows us to see at a glance that something is wrong. If you see a function that starts with a capital letter being invoked without a new operator, it is a clue that it's a mistake. In JavaScript, functions have a special property called prototype that's only meaningful when the function is used in an object constructor. Prototypes allow related objects to share functionality, and it also makes inheritance possible in JavaScript. Let's first add some functionality to our cart object without prototypes and see what happens. I'll edit a file called cart.js, and I'll create a constructor function, same as from previous lessons. And this time I'll add a function called total, which will total the value of the items in the cart. Now our carts have the ability to calculate the total price of what's in the cart. Notice we use JavaScript's built-in reduce function to calculate the total. It's beyond the scope of this lesson to describe how reduce works, but it's a very handy function and I recommend you read up on it. You could just replace this with a for loop that updates a sum. That would accomplish the same thing. Now let's give our new functionality a spin. I'll exit that file, I'll start up Node, and I'll load cart.js. I'll go ahead and create a new cart, call it cart1, and I'll add a couple of items to it. Now if I look at my cart, I can see it has my items in it, and if I call cart1 total, I can see it sums the items in my cart. So far so good. Now let's create a second shopping cart. I have a new cart that doesn't have anything in it, and if I call its total function, it returns 0, as I expect. So you can see that the two carts have different items and different totals. It would be nice to have a convenience method to add an item to the cart, though. We know that we can modify objects directly, so let's try adding it to cart1. I'll call it addItem, and all it is a function that takes an item and adds it to the object's items array, just as we were doing manually before. So now I can call cart1 addItem and add a new item to it. And if I look at my cart1, I can see those items are in it. The problem is, though, the addItem method only exists on cart1. Let's see what happens if we try to do it on cart2. Node gives us a no method error. That's because cart2 doesn't have the addItem method. We can, of course, manually transfer the function over to cart2. We can say cart2 addItem equals cart1 addItem, and now if we go back and try it again, we can see cart2 addItem works as expected. There must be a better way. We could modify the cart constructor and add that function, and any new carts would have the function, but the existing carts still would not. This is where the prototype property comes in. Every function has a property called prototype. When you use that function as a constructor, that prototype is attached to the newly created object, and that object has access to the properties of that prototype object. Let's see how we can use cart.prototype to add functionality to all instances of carts, even existing ones. Let's say we want a convenience method to empty the items in the cart. We'll add it to cart.prototype. So notice we simply said cart.prototype.empty and created that function. That is, in essence, adding an empty method to cart.prototype. Even though we created cart1 before we created this method, we can still call it on cart1. No error. And if I look at cart1, the items array is empty. That's because every instance of cart has a reference to the cart constructor's prototype object, and there's only one of them. So if you add something to it or modify it, it immediately becomes available for all cart objects. Defining methods on the constructor's prototype has two additional advantages over defining methods in the constructor. First, it is more efficient. If you define a method in a constructor, a new function is created every time you create a new object. Multiply the number of methods your class has by the number of object instances you expect, and that could be a significant number. Using the prototype ensures that functions are only defined once and shared by all instances of that class. Secondly, if you need to modify or fix a method on the fly without destroying and recreating existing instances, you can do so using prototype, since all instances share the same prototype object. Let's rewrite our original cart class using prototypes. I'll exit node by typing Ctrl+C twice, and I'll edit my cart.js file. You can see here we have the total function inside the cart constructor, so every time we construct a cart object, it gets a total method. So let's take that and move it outside of cart. And obviously we don't have this available, so we'll say cart.prototype.total equals function, and the function doesn't change. Let's load it up in Node and make sure it still works. I can look at cart1, I can see that it has an item in it now, and I can call cart1.total, and it will tell me the total of the items in the cart. And that total method is on the prototype object. As a general rule of thumb, value properties should be added in the constructor, and methods should be added to the constructor's prototype. You should have a very good reason if you're going to break that rule. In addition to providing method reuse among object instances, JavaScript's prototype mechanism is chained, which allows JavaScript to implement inheritance. Inheritance allows you to have levels of abstraction in your object model. For example, a gas-powered car is a wheeled vehicle, which is a land vehicle, which is a vehicle. In object-oriented parlance, gas-powered car is a subclass of wheeled vehicle is a subclass of land vehicle, and so on. At each level, functionality is available to subclasses, but not superclasses. For example, vehicle may have a method called getMaximumSpeed, which is then available to all subclasses, down to gas-powered car. Air vehicle, which is a subclass of vehicle, may have a method called getMaximumAltitude, which is available to its subclasses, but is not available to vehicle or general subclasses of vehicle. Some object-oriented languages support the concept of multiple inheritance, where a single class can inherit from multiple parents. JavaScript does not support multiple inheritance through its prototype chain, though it does have even more powerful ways to inherit functionality from other classes. Let's see how the prototype chain works. We'll fire up Node and create some classes and subclasses. We'll start by creating some constructors for some animals. We'll have a generic animal, we'll have a mammal, and we'll have a cat. So far, we only have 3 unrelated classes. Let's establish an inheritance hierarchy. To do that in JavaScript, you have to create a new prototype for subclasses based on superclass prototypes. JavaScript has a built-in function, object.create, that will do that for you. We'll start by making mammal a subclass of animal. Note that we don't just set mammal.prototype to be animal.prototype. If we did that, a mammal couldn't functionally be distinguished from an animal, because they share the same prototype object. Now let's make cat a subclass of mammal. Note that the order is important. If we had done this the other way around, when we changed the mammal prototype, we would be breaking the connection between mammal and cat. Now that we've got an inheritance chain set up between our classes, let's add some appropriate functionality to each class. All animals can eat. We'll give that functionality to animal. Mammals uniquely can produce milk, so we'll have a function called milk. Mammal singular, not mammal plural. And then finally, cats have claws, so let's say cats can claw you. So now that we have some classes and an inheritance hierarchy, let's create some instances. My cat's name is Sam, so let's create a cat to represent my cat. And we'll also create some generic animals. I'll have a generic mammal and a generic animal. I'm not going to give them names the way I give Sam a name because they're generic. Let's see what Sam the cat can do. Sam can claw, Sam can milk, and yes, Sam is Samantha, a girl, and Sam can eat. What about our generic mammal? If we try to call claw on that, we'll notice that the generic mammal can't claw. That's because only cats can claw, and generic mammal is a superclass, not a subclass of a cat. However, our generic mammal can't milk, and it can't eat. Lastly, we have our generic animal. Unsurprisingly, it can't claw, because that's something only cats can do. It can't milk, because only mammals can milk, and there are types of animals that are not mammals. But we know that all animals can eat, so our generic animal can eat. Note that when you try to access a property of an object, JavaScript walks the prototype chain backwards, starting with the most specific prototype. For example, if I say sam.eat, JavaScript says, does cat prototype have an eat property? No. Does mammal.prototype have an eat property? No. Does animal.prototype have an eat property? Yes, this is the one. The consequence of this is that prototypes lower down in the prototype chain will mask properties higher up in the prototype chain, which is what you want. For example, if we want cats to eat differently, we can say cat.prototype eat, and we can give it a new function. And now when a cat eats something, like Sam, you'll notice it's pulling off the function from the nearest item in the prototype chain, which is cat.prototype, instead of pulling it from animal.prototype. But generic animals still use the function prototype from animal. So we see that cat.prototype.eat is shadowing animal.prototype.eat. All objects in JavaScript have the generic object prototype, object.prototype, in their prototype chain. Object prototype defines such methods as toString that are available to all objects in JavaScript. For example, even though I didn't define a toString function on cat, I can say Sam toString, and that function does return a string, even though it's not very interesting. Just because JavaScript doesn't have the concept of a private object member, like some other object-oriented languages, it doesn't mean JavaScript doesn't have a method for data hiding. We already know that JavaScript has function scope, and variables declared in a function can't be accessed outside of the function unless the function explicitly makes them available. We can use JavaScript's function scope, which creates closures, to hide functionality in our objects. Let's look at an example of data hiding in our cart object. Let's imagine that we want to make our cart object really safe, because we're going to be turning it over to some junior programmers, and we want to make sure they don't make any mistakes that could cost us money. Until now, we've been storing items in an array that's a property of cart, but that means that anyone can modify that array and possibly cause problems for our cart object. To make our cart object safer, we'll move the list items into a closure and provide a public method for adding items. I'll edit a file called cart.js, and we'll create our object constructor as normal. Create an items array. Go ahead and type this out, and then we'll explain it in a second. So what we've done is we've created two methods, getItems and addItems. You'll notice this is a little bit different than how we've done it in the past. Instead of saying this.items, we have var items there on line 2. So var only lives within the scope established by the cart function, meaning it can't be accessed from outside that scope. Notice that on line 5, we don't just return the items array, because then the items array is able to escape the scope of cart and someone could modify it. Instead, we call items.slice. If you call that with no arguments, it essentially creates a shallow copy of the array, and you can modify it to your heart's content. I'll start up Node. I'll load cart.js, and then we'll create a new cart. And we'll go ahead and add an item. Looks like we made a mistake in our cart definition, so let's edit that real quick. Start up Node again, load my cart object, create a new cart, and add an item. Now you'll notice that if I type cart items, that's undefined. That items variable is inside the closure created by the cart constructor. We can get the list of items using the public method, so I'll set up my own variable. I'll call it items outside just to distinguish it. I'll call cart.getItems. And if I look at items outside, I'll see that broccoli is in there. Let's see what happens when we try to modify that array. I'm going to take items outside, and I'm going to push something onto it. And just because I'm intentionally trying to mess things up, I'm going to push something that doesn't look like an item. I'll just say I'm not an item, so I'm just pushing a string onto that array. So now if I look at items outside, you can see there's something that looks like an item and something that doesn't look like an item. If we were modifying the items array inside our cart, this could cause problems for our shopping cart. But let's see if shopping cart knows about this. I'll call cart.getItems, and you'll notice that the I'm not an item string is not in the cart. So we successfully managed to isolate the items array from external influence. However, this has come at a cost. Note that we must define the public methods for our object in the constructor. We can't define them in the cart's prototype object because then they wouldn't have access to the closure. In JavaScript, this is the trade-off required for effective data hiding. It may feel like classically object-oriented programming is a little tacked on in JavaScript. There's some truth to that. JavaScript really isn't a classically object-oriented language. And while it can emulate much of the behavior of a classically object-oriented language, it is more awkward than using mixins and closures, which are more natural to JavaScript, and we will be talking about later. However, JavaScript can be quite capable as a classically object-oriented language, and you can make it easier by creating some helper functions to smooth out some of the rough edges. Some people advocate for the use of a helper function to attach methods to a class's prototype. For example, I'll create a file called extends.js. So this is the helper function that Douglas Crockford recommends. It allows us to attach a method to an object prototype. For example, instead of typing something like this, we can instead write this. This can be handy if you have a large number of short methods to add, but generally I feel it's just as easy to add methods to your class's prototype in the normal fashion. A more useful helper function is the fiddly business of setting up a prototype chain. In previous lessons, we saw how to do that, but we omitted a step because it didn't affect our discussion, but for completeness sake, we'll include it here. I'm going to delete this code because we won't be using it, and we'll recall our example of animals. To hook up our inheritance chain, we did this. We set the prototype of mammal to be an instance of animal prototype, and we set the prototype of cat to be an instance of mammal.prototype, thereby establishing the inheritance chain. The step we skipped was correctly referencing the constructor function. Object.create will copy all of the properties, including a reference to the constructor function that is used to create objects of this type. Many times, it's okay to skip this step, but some libraries use the construction property to infer information about inheritance, so it's best to add it anyway. Let's go ahead and modify this to include that step. This makes sure that the constructor object is set correctly for mammal and cat, which otherwise it wouldn't be. This is a lot of detail to remember. We can create a helper function to do all of this for us. Normally, you have to be very careful about modifying built-in JavaScript objects, such as function, but setting up an inheritance chain feels very natural as an extension to function.prototype. Let's see how it works. I'm going to go ahead and add it here below. I'll say function.prototype, and I'll call it extends. Different people have called it different things, but extend seems the most natural to me. And you take the superclass that you intend to extend. We'll set the prototype to be a new object created by object create based on the superclass's prototype. And then we'll set the constructor to be this function. Now we can set up our inheritance chain more naturally. Instead of saying mammal.prototype and mammal.prototype.constructor, and the same for cat, we'll just delete those. And now we can simply say mammal extends animal and cat extends mammal. Now it's much simpler and much more clear. You can see at a glance that mammal is intended to be a subclass of animal and cat is intended to be a subclass of mammal. I misspelled extends there, let's correct that. Note that the order in which we do this is still important, and we still have to do this before we add any methods to the prototype of mammal or cat. I'm going to include extends.js in the working files for this chapter, as we'll be using it again. Due to JavaScript's prototypal object model, classically object-oriented programming can feel overly complicated. In ES6, the fundamental prototype nature of JavaScript hasn't changed, but some syntactic sugar has been introduced to make it feel a little more natural. Syntactic sugar is just a way of saying syntax that doesn't fundamentally change the way a language works, but it makes it easier to accomplish certain tasks. In the case of JavaScript, let's look at a class definition in ES5. I'll just create a test.js file, and this is how class definitions look in ES5, which we've already covered. We can have an animal that can have a property, generic animal, and animal.prototype.eat, method, and then we can have a mammal, generic mammal, and mammal.prototype. We'll make this a subclass of animal, and we'll set the constructor, and lastly we'll give it a method. Notice that we have to define the methods after we establish the prototype chain. I won't continue this example on for cat. This has all the examples we need here. So that's the way we do it in ES5. It's the way we've been doing it throughout this course. But in ES6, we have a more compact syntax. I'm just going to draw some lines here to represent that everything above the line is ES5, and this is how it will look in ES6. So these are exactly equivalent, but you'll notice that the ES6 is a lot easier to read, it's a lot clearer what's going on, and there's a lot less fiddly syntax to establish our prototype chain and our methods, but nothing fundamental has changed. We still have prototypes. Inheritance still works exactly the same way. The syntax just makes it easier to construct this. So just to do a quick review of how it works in ES6, we have a class keyword, which we can use to establish a class. The constructor takes the place of the constructor function in ES5. So we would put any property definitions here as we have on line 17. And we no longer have to access the prototype to establish methods. We can simply declare methods inside the class. They are added to the prototype just as they are in ES5. We just don't have to do that manually. And then lastly, to affect the prototype chain, we can use the extends keyword. You'll see here on line 24 that class mammal extends class animal, making mammal a subclass of animal. The same thing is happening. We're setting the prototype using object create, and we're setting the prototype constructor, but we're doing it the ES6 way, which is a lot less wordy. In a strongly typed language like Java or C#, it's easy to classify objects because they have a concrete type or implement a concrete interface. In JavaScript, it can be difficult, and sometimes even impossible, to tell what type an object is. In many ways, it is better to give up fighting JavaScript's loosely typed paradigm. Once you do, you'll find that not thinking in terms of types can be incredibly useful. Before we talk about duck typing, let's review the mechanisms that are available for identifying types in JavaScript. We'll start Node, and we'll talk about the typeof operator first. We'll create a few variables of different types, a number, string, object, and a function. Now let's see what the typeof operator returns for each variable. Typeof_in tells us it's a number, typeof_s tells us it's a string, typeof_o, object, typeof_f is a function. So the typeof operator is telling us exactly what we want to see. Now note that typeof is an operator and it's not a function. Very often you'll see code that looks like this that works, but it's actually not necessary. Really all you're doing is creating a parentheses group that is then applied to the typeof operator, so it's not actually necessary. You can omit the parentheses. So far so good for the atomic types. We've identified numbers, strings, objects, and functions. You'll notice we've omitted arrays. There's a good reason for that. Let's go ahead and create an array and see what typeof says. Objects. This is one of JavaScript's trickier aspects. Arrays are objects, special objects, but still objects. It would be nice if typeof identifies arrays as such, but there's too much code out there that relies on this behavior to change it now. We'll come back to this. Our second method for determining type in JavaScript is the instance of operator. If you have correctly constructed classes, you can use the instance of operator to determine if they were created from that class prototype. Let's create some classes. We'll use the animal example we've been using. Class called animal. Try that again. Give it a body, even if it's empty. And I'll create a class called cat. And I will make cat a subtype of animal. And just for completeness, I will assign the constructor. Now let's create a couple of instances of our new classes. I'll create a variable called a, which is a generic animal. And I'll create a variable called c, which is a generic cat. Now if I type typeof a, it simply tells me it's an object. Ditto typeof c. So typeof isn't much help here. It's not telling us what specific type of object it is. We can, however, find if they're instances of a specific type of object. For example, I can say a instance of object. And that's not telling us much though. However, if I say a instance of animal, we can see that a is indeed an instance of animal. We can see if a is an instance of cat and is not, because cat is a subtype of animal. C, on the other hand, is also an object. C is an animal, and C is a cat. So if you're looking to see if an object is a specific class type, you can use instance of to determine that. You'll use typeof a lot, and perhaps instance of, depending on how object-oriented your project is. But there's another option in JavaScript called duck typing. The idea behind duck typing is that if something walks like a duck and quacks like a duck, then it's probably a duck. Let's go back to the example of arrays, which can't be distinguished by typeof. Create an array again, and we say typeof a, and it simply tells us it's an object. There are two built-in ways in JavaScript to determine if something's an array. We can say a instance of array, and it will return true, indicating that this is indeed an array. We can also say array is array, a, and it will return true. So we have two ways to determine if something's an array. However, let's imagine for a moment that we didn't have these options. How might we determine if a is an array? Well, we know that arrays have a length property. So if I say a.length, it doesn't return undefined, it returns 0. So we could use this to make an assumption that a is an array. Arrays also have a function called push. If I say a.push, it tells me that there's a function attached to a called push, which is again an indicator that this is an array. Once again, the fact that a.push exists and is a function points to the fact that it's an array. Of course, we could create an object that would fool this test. Looks like I left off a pair of curly brackets. Let's try that again with the correct curly brackets. Now we have an object O, and if I look at O.length, it's a number, and if I look at O.push, it's a function. So if I were just relying on the existence and correct type of length and push, I might come to the conclusion that O is an array when it actually isn't. So duck typing is at once beautiful and dangerous. It is dangerous because it can be fooled. If you really absolutely need to know something is of a certain type, then duck typing might not be the best bet. Instance of will probably serve you better. Duck typing, on the other hand, is beautiful because sometimes what's important is what an object can do, not what type it is. For example, if you want an object that you can add things to, and you verify that there's a push function, does it matter if it's an array or an object with a useful push function? You can actually use that flexibility to your advantage, and then it becomes a matter of using things based on what they can do, which is quite powerful. Object-oriented languages like Java and C# have the concept of interfaces, which describe data or functionality that an object must support. Interfaces are handy when not everything fits neatly into an inheritance hierarchy. For example, a bird and a plane may not inherit from one another, but they both have the ability to fly. Behavior injection allows you to provide interface-like functionality in JavaScript. In many ways, it's more flexible than interfaces, as you can control exactly what behavior gets injected and how it gets injected. Behavior injection is often called mixing in, or mix-in for short. In JavaScript, there are many methods available for behavior injection, from extremely simple to very abstruse. However, the idea is the same in every case. Behavior is copied from one place to another. Usually it's copied in logical groups to class prototypes, though that is not a requirement. I prefer to keep my behavior injection mechanism very simple. Let's take our example of birds and planes and see how behavior injection works. We'll start up Node and create some classes. I'm going to use the extends.js file from chapter 5, which I've copied into the working files for this lesson. And then we're going to create some classes. I'll create one called vehicle, and then I'll create one called plane, and then we'll have plane extend vehicle, and then we'll create a generic animal, and then we'll create a bird, and we will have bird extend animal. So you can see that bird and plane both live in different inheritance hierarchies. Bird derives from animal, plane derives from vehicle, and neither vehicle nor animal derive from the same thing. So they don't share a common ancestor. Since they don't share a common ancestor, there's no obvious place to implement a fly method. We could, of course, artificially create a common ancestor, call it thing, and give it the ability to fly, but there are lots of things that can't fly, and this is where behavior injection comes in. Let's create a function that adds the ability to fly to something. I'll call it addFlight, and I'll take a single argument O, and whatever O is, it'll add the ability to fly to that. So I'm going to say O has a function called fly, and for now we'll just return a string. Let's also add the ability to land, so we'll have a class called land, also a function that returns a string. And then we'll end our function. We have a function called addFlight that will add the ability to fly to whatever you pass into it. We could use the addFlight function to add flight to individual object instances. Let's give that a try. I will create a plane that I'll call plane1, and that'll be a new plane. And bird1 equals new bird. And I'll create a second plane. So now I have two planes and a bird. Add flight and pass in plane1, and now plane1 can fly and it can land. The problem is plane2, which is the same type as plane1, can't fly. Get an error because there's no fly object. Of course, I could call addFlight to plane2, but really I want all planes to have the ability to fly and land. Fortunately, we can do this by calling addFlight and passing in the class prototypes. So I can say addFlight plane.prototype, and I can do the same on bird.prototype. So this is adding those functions to the prototype objects for plane and bird, meaning it will be available to every instance of plane and bird. We already have a instance of bird which we had not called add flight on, so let's see if bird1 can fly now. Sure enough, bird1 can fly, because all birds can fly. We can create a new bird and see if that can fly. Behavior injection goes hand in hand with duck typing. When we inject behavior into an object, it is more about the behavior than the type of the object. In this case, we can call add flight to any object, regardless of its type. So if we need to determine if an object can fly, we care less about what kind of object it is, and more about whether or not it has a fly method. For example, I can say, and that will determine whether or not bird2 has flight. And bird2 indeed has flight because all birds have flight. With any technology, it's reasonable to ask what benefit the technology is bringing to the table. Let's review the reasons that make object-oriented programming so valuable. Object-oriented programming solves problems in a way that's natural to humans. It's one of the reasons that object-oriented programming has enjoyed so much success. An object, like a car, has properties, make, model, etc. A car also has functionality, like drive, park, etc. Entire classes of objects, like cars, share the same properties and functionalities. And classes of objects are extensions of more general classes of objects. For example, a car is an extension of a vehicle. This is a natural way to think about and approach problems, which makes object-oriented programming very powerful. Object-oriented programming provides a logical way to package code. Objects are self-contained. If designed well, they can be reused without modification. It's important to note that, like any tool, it's only useful if it's used well. Objects that try to do too many things will often have to be modified to work in new environments, reducing their value as a code reuse vehicle. Object-oriented programming provides a good framework for code reuse, but it's up to you to design objects that are general enough to be reused. Lastly, object-oriented programming makes it easier to transition to other object-oriented languages. Most of the major programming languages in use today support object-oriented programming in some way. Once you learn the principles of object-oriented programming, it gives you a leg up in learning another object-oriented language. You've already got the big picture. All you have to worry about is syntax and details. JavaScript is a multi-paradigm language. That means it gives you the ability to not only use different paradigms in your software design, but to mix and match, using the best paradigm for the problem at hand. This can come at a cost. If there's not a unified architecture to your software that somehow ties the use of multiple paradigms together, the use of multiple paradigms can produce confusing software that's difficult to scale. If you're just beginning your programming career, you might want to pick one paradigm and stick with it. Once you have some more experience, you'll see where it makes sense to introduce other paradigms into your design. Let's wrap up this course with a review of using 3 different paradigms to solve the same problem, the creation of a shopping cart. We'll start with procedural programming, which represented the dominant paradigm before object-oriented programming came into the picture. Create a file called cart.js, and I'll create an array to store my items, and a number to store the total. And I'll create a function called addItemToCart, which will take an item and add it to the cart, take the items and push the item onto it, and increment the total. So this is a procedural approach to the problem. This code isn't easy to reuse. Right off the bat, we see that it's hard to make more than one cart. We would have to have a different items array for every cart. But the function addItemToCart would always add things to the same cart. Furthermore, if you copied the function without copying the variables, it would break when you tried to call items.push. There are ways that we could clean this up without making it object-oriented, of course, but objects provide such a clear and straightforward mechanism, we'd be silly not to use it. Procedural programming isn't inherently bad, and there are situations in which it is very useful, but it has some limitations for designing large systems. Let's see how we can rewrite that code to use a classical object-oriented paradigm. I'll delete that, and we'll start again. We'll create a class constructor for our cart. We'll initialize an array of items inside the cart. We'll initialize the total to 0, and then we'll create a method on it to add items. What we've done is very similar to what we did in the procedural case. Except this time, our code is bundled neatly together in an object, and we can create as many carts as we want without having to worry about which items array our addItem function is pointing to. So now we have much more portable code. All we have to do is export this class, and we can create as many carts as we want, and they will all be self-contained and have the same functionality. We're really doing prototypal object-oriented programming here, but we're doing it in such a way that it emulates very closely classical object-oriented programming available in other languages. What if we wanted to use closures instead? Still object-oriented, just not using traditional paradigms. Let's rewrite this using closures. With a closure, we have a function called getCart, which is similar to an object constructor. However, it doesn't create an object in the usual sense. You don't use the new keyword with it. We create an array of items, we create a total, and we return an object, an anonymous new object that isn't associated with any class, that has methods for adding items. And we'll add a method to get the total. What we've lost here is that we're creating a new addItem function every time we create a new cart. But what we're gaining is some protection. The list of items and the total can't be modified outside of your cart code, which may be desirable. You should now have a good understanding of object-oriented programming and how it is implemented in JavaScript. It's an incredibly powerful programming paradigm that has the potential to make your software easier to write and understand, and more robust. JavaScript gives you a lot of options for implementing object-oriented design. So go make something great.